close that and bring that. This is the third part to Unit 1. All right, there's only 3. Now the rest of the units now move quite quickly. All right, and in Unit 1, and I'm sure different teachers teach it differently, but in Unit 1, and I'm going to do a quick little recap of what we did. In Part 1, we learned about the atoms and all the parts of the atoms, right? The electrons, the protons, the neutrons, and all that type of stuff. And we learned just about the atoms themselves, the properties of the elements, right? And then in Part 2, we learned about what happens when you put the atoms together. When you put, right, metals with nonmetals, you get ionic compounds, and when you put nonmetals with nonmetals, you get covalent compounds. We talked about the way they bond, ionic bonding or covalent bonding or molecular bonding, right? Single bonds, double bonds, triple bonds. So in Part 2, we talk about what happens when the atoms get together. In Part 3, we're going to talk about what happens when the compounds get together. Can they rearrange and undergo chemical reactions? And the answer is yes, right? But some teachers will squeeze that into like a shorter, like about half the time, and they'll very quickly go over the atoms and very quickly go over compounds and very quickly go over the reactions. But I feel it's important enough that we spend a little bit more time on this, and that's why Unit 1 is all stretched out, and then Unit 2, Unit 3, and Unit 4 are quite quick compared to it, but that's why. So this is Part 3 where we're talking about chemical reactions. And so let's just talk a little bit about what a chemical reaction is. No need to rewrite chemical reaction because you just wrote that down. So here we're just defining reactants and products, starting material reactants, the new substances produced, the products. And we can tell that we've had a chemical reaction because the physical properties of the products are different than that of the reactants. We talked very briefly at the beginning about chemical change. That's what we're looking at very closely in this part of the unit. Chemical change, and then more specifically, how we can write the balanced chemical equations for these chemical changes, these reactions. Now, again, I want to stress that the stuff we do today, you're not studying that for the test. You're studying the stuff that came before it, up to that naming of molecules. With you sitting right up front, Jess, and you like following your notes and just staring at me, I'm a little weirded out right now, the way you're just kind of, go ahead. I'm ready for the next thing. I'm just joking. We could rearrange if that is better for your learning style. Okay, are we good to go on that one? All right. So let's just remind ourselves of the evidence of chemical change, because we will be looking and doing various reactions. And again, what we're doing today is we're just learning about balancing. We're going to practice some balancing. And then after the test on Tuesday, so next week, Wednesday, we're going to start looking at the types of reactions. And you did this all in grade 10. You would have talked about synthesis reactions and decomposition reactions and combustion reactions and single displacement reactions and double displacement reactions. So we're doing all that stuff that you did in grade 10, except it's going to be in more detail. We're going to teach you a few more things on how we determine a successful reaction or not. So again, reminder of evidence of chemical change so that when we make our observations, we know what evidence to make reference to. And you will be writing this out many times in our labs. It'll say, how do you know a chemical change took place? And you're going to make reference to one of these. Of course, I'm hoping that you're beginning to realize I want specific reference, right? So let's say that it changes color. You're going to say, you know, a chemical reaction took place because a color change was observed. And then you're going to say, as can be seen by, and then you're going to tell me a specific example. That's how you get those 4 marks, like on that last lab you just did. You know, tell me how ionic compounds are similar to molecular, and then support it with evidence. So then you say, as can be seen by, and you give me specific evidence. That's how you do that. So again, if you see the formation of gas, you'd say, as can be seen by the fact that, and then you'll tell me what the reactants were, produced lots of bubbles, right? You're going to give me the specific evidence. Formation of a precipitate, as can be seen by, and then you describe the reaction, and then you tell me what precipitate you observed. Production of light, we're not going to do any reactions that produce light. There is one that we do have the chemicals for it, but to be honest, I've never tried it, and that's not true. I tried it, and I failed miserably at it. You can mix these various chemicals together to produce a similar type of chemical that's in those glow sticks, right? And when you mix the two together, you can get this beaker to glow. And a young student teacher that was here about 4 or 5 years ago showed me, and I'm like, whoa, that's awesome, I got to try that. She left me the recipe, and I failed miserably at it. It didn't glow at all, so I'm not sure how to do that. I'm going to have to figure it out. But we're not going to be looking at any examples of light production. Exothermic, X to exit. That means that the chemicals have given off heat, thermic, like a thermometer. And some reactions can be endothermic. That means like an entrance, it goes in, the heat comes in, and that is cold and it absorbs heat. So again, you've written those things down before in the past. This is just a reminder so that when we get to the lab, you are reminded of what you can make reference to. Again, we've got various devices going, we've got thumbs up all around, we're sending texts back there. That's good. That means you're done writing, I take, right? Oh, well, that also means that you're done writing. But that doesn't mean you should be sending text messages. All right, so how do we represent a chemical reaction? There's 2 ways in which we can represent chemical reactions. We can do it with word equations, and we can do it with balanced chemical equations, and today's lesson is on balancing. The proper way in which we represent a chemical reaction, reactants on the left, the arrow to represent the reaction taking place, and products on the right. And again, I'm speaking this with a tone of voice almost as if to say, you've seen this all before, and I am correct, right? This is something you do in grade 9 a little bit, you're introduced to it. Grade 10, you might even do a little bit of balancing. And then if you've taken the grade 11, you've seen balancing again, the grade 11 university, and now here in the grade 12, we're going to be doing more balancing. Now I'm going to be teaching you really a vastly different way to balance, and I hope it works for you. This is the way I teach the grade 11 university class. That doesn't mean it's a hard way, but it's got some shortcuts, right? Because I'm sure in the past you've done lots of counting. Let's count all the H's and let's count all the N's and make sure all the numbers are the same, right? There are other ways to balance that use some other logic than just counting. In the end, it still results in the same. You should have everything balanced. But we do know a little more about chemistry this time than we did in the past, so we can kind of extend the way we do things. So here we've got a simple word equation that represents the reaction between hydrogen gas and oxygen gas. The hydrogen and oxygen get together, and it forms water. So that is our word equation. Again, I'm not sure where people are at. We've got people with slides. That's cool. Let me know. If I click and you're writing off of the television, that's terrible, why did I say that? You're writing off the screen, then let me know to go back, okay? So, again, you don't have to write representing chemical change again. We're now at the subheading chemical equation. uses the chemical formula of the reactants and the products to represent the chemical equation. And this particular one is not balanced. So this is not a balanced chemical equation. My next slide, I'm going to talk about why we need to balance a chemical equation, and then we're going to balance some. But there's no reason why we couldn't try to balance this. We've seen these types of equations before, and if you feel you know how to balance that, go ahead and give it a shot. And we're going to be doing lots of balancing here in a moment. So when you go to try it before I give you the answers, get your pencils out, right? That's what I always say. Use pencils. Then if you make the mistake, you can always fix it. And if you need a pencil, I put a few of them right here by the sharpener, because for some reason students don't actually know how to use my sharpener, so I supply you with some sharpened pencils. Again, I have no idea where you're writing, but has anybody attempted to balance this? Anyone? Anyone? As I look at the back towards Alexis? What do we have to do to balance chemical equation? What do we have to do? Yep. Make it even on both sides. I like that term. Make the numbers and types of atoms the same on both sides, right? So the same number of hydrogens and the same number of oxygens. Excellent. So we've got 2 hydrogens in an H2. And we've got 2 oxygen atoms in an O2. And there are 2 hydrogen atoms in a water and 1 oxygen atom in a water. You'll notice here, I think you notice, that the oxygens right now are not balanced. Does that make sense? Okay. So if I want to get 2 oxygens, what number am I going to have to put up on the front here in order to balance that? Just to balance the oxygens, I need 2, because I've got 2 on the left. What am I going to have to put in here to get 2 oxygens? What do I have to put? Oh, no, veterans aren't allowed here. Veterans get to rest. What are we doing? Bethany, what do you think? We see here, are we okay with the fact that that represents 1 oxygen atom? Does that make sense? What's that? You put like a 2. Remember doing that before? You put a 2, and you put a big 2 out front. That's okay. That's why we're going to practice this. This is just a little dry run. But you're right. I've got 2 of them here. There's only 1 here, so I'm going to need 2 of these water molecules in order to generate 2 oxygen atoms. Make sense? Okay. Let's now take a look at our hydrogens. Because I put a 2 there, this now represents our 2 oxygens, which is good. So now how many hydrogens are there in 2 water molecules? Yeah, there's 4. 2 times 2. So there's going to be 4 of them. 2 water molecules, 2 times 2, 4 hydrogens in that thing. Okay? All right? Let's go back and look at the hydrogen. How many hydrogens do we have right here? There are 2. 2 hydrogens. So how many H2s am I going to need to balance up the H's on the other side? Bethany, what do you think? We're going to need 2. That's going to be 2 times 2 is 4. Excellent. 2. So there is the essence of some very simple, straightforward balancing. And that's good. That's important. We're going to have to do that. Okay? So just a reminder, and I'm going to go through this, we've got these big things here called the coefficients. And these coefficients tell us how many of those molecules we have. 2 water molecules. We also have the little numbers. They're the subscripts. And they're going to tell us how many of those atoms are in each molecule. When we put a coefficient with a molecule, we multiply the coefficients by the subscripts. So 2 times 2 is 4 hydrogen atoms. And 2 times 1 is 2 oxygen atoms. Are we okay with those kind of basic ways in which we add and count things? Because if you've got that down, then we should be in good shape. So let's move ahead. And let's talk about why we balance them. And we've actually just done this. We put the coefficient in front of the molecules in order to balance it. Why do we balance it? We balance it because we have something called the law of conservation of mass, or the law of conservation of matter. It says that if we have a chemical reaction, we can't gain or lose anything. We can't have atoms magically appear out of nowhere, and we can't have atoms magically disappear into nothingness. Chemistry isn't magic, even though it seems pretty cool sometimes. You know, you might think it's magic, but it isn't. So we must have the total mass of the stuff on the left be equal to the total mass of the stuff on the right. And the way we do that is we put the big numbers in front of the chemicals. We call the coefficients, the coefficients, that's what they're called, are those big numbers that we put in front of the chemicals. All right? And that's how we balance it. Now, when I teach the grade 10s sometimes, and when you teach the grade 10s, it's really the first time you've seen balancing, I will often say to the grade 10s that when you're balancing, right, you can change the big numbers, all right? So you can change the big numbers. The coefficients that we put in front, you can erase those, change it, you can do whatever you need to do to the big numbers, but you cannot change the subscripts. They're locked into the identity of the chemical. So you can change the big numbers, but do not change, and I would say to the grade 10s, the little numbers, which they're the little numbers, but they're the subscripts, right? They're those the little numbers. So I'm going to put in there the little numbers, all right? And again, that just kind of helps you out because, again, I find, especially with the grade 10s, when they get balancing and they get stuck, I find some of them will just change those little numbers all around. And when you change the little numbers, you're actually changing the identity of the chemical. It would have a different name. It would have different properties. So when we're balancing a reaction, we can't just, at our own choice, change the identity of the chemicals because that wasn't what the question was that we were given. So we can only change the big numbers. Okay? Now, you learned how to balance probably some very simple ones in grade 10. Now we're going to be dealing with more complicated type chemical reactions. And some of them are going to have polyatomic ions like sulfates and carbonates, and they're going to have lots and lots of different types of atoms. And if we simply count each atom, it's going to get very confusing and it becomes very difficult. So I have a list of tactics or little kind of plans that I found to be useful in balancing. And some of them, like this last one, actually breaks one of the rules that we have for balancing by using a decimal or a fraction, but I'm going to show you how we then can fix it to make it a proper balanced chemical equation. Because I don't know if you recall back to the last time you balanced, but the most frustrating thing is when you get to the end and you're trying to put that last number down and you have 7 of them and then you've got an even number and you can't make it work because the math doesn't work, so then you just throw it out and you say, this sucks. So I'm going to show you a way in which we can do a little cheat move by using a decimal, and the decimal will always be 0.5. It'll always be a half of a molecule, and that will then allow us to fix this problem, okay? Now, I don't know of any textbooks that have these particular tactics in them. These are ones that I've come across that I find is useful to me. When I'm having to balance a whole bunch of them up, say I'm doing a mark sheet or something, these are the plans that go through my head when I go through them. So, balance any elements that are alone. Balance any elements that are alone. Do them last. Because if you put a number in front of it, you don't change anything else. It just changes that thing. So if you've got like metals, do them last. If you've got a Hofbrinkel, do it last. If you've got a metal and the Hofbrinkel gas, do the metal last and do this one second last because it's got a 2 with it, right? So you gotta kind of do it in order, but do anything that's by itself last. If we have polyatomic ions, brackets with say a CO3 or something in it, they tend to stay together. So you'll find that you've got a carbonate on one side and you've got carbonate on the other side. don't separate them out into C's and O's. Treat them as carbonates. So you might have 2 carbonates over here, 1 carbonate over here, put a 2 to make 2 carbonates. Don't separate them out into their individual atoms because you'll be counting forever. So leave them together if they're together. Very often we will find on one side we'll have 2 of one thing and 3 of the same thing on the other side. And it's very difficult to balance 2 and 3. Just swap the number over. Put a 3 in front of the one that has a 2, and put a 2 in front of the one that has a 3, and you've automatically created 6 of them, and they become balanced right away. So if you find on one side you've got 2 irons, Fe2 something, 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 and the other side you got 3 irons, Fe3 something, 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 put the 2 there and the 3 there, and you'll have 6. And you'd think you could do that with other numbers, but we see the 2, 3 example over and over again. It seems to come up in chemistry all the time. I say that if you're dealing with like a Hofbrinkel gas and you've got a 2, sometimes if you could just have a half, like a half of an oxygen molecule, let's say you just need 1 more oxygen atom and it would be balanced. But they only come in pairs. Well, if you had a half of an oxygen molecule, that really means 1 oxygen atom. And if you use a half as the coefficient, say 2.5 oxygen O2s, which are 5 oxygen atoms, it'll make your balancing easier. Now, the official rules of balancing are that you can't have a 0.5. So what you do at the end is you double every number, and it gets rid of the 0.5. So again, it's a little mathematical trick. Okay, so these are, like I said, little tricks that I've come up with that help me balance, and hopefully they'll help you balance. Okay, so let's just do some examples, e.g., and we will start, oh, we did that one. I forgot that was my first example, and yeah. Actually, you know what? Let's use one of our tactics to balance this, different than the way we balanced it the first time. So let's use one of our examples. So we've got writers as well as people with, and I want everyone to keep up because I want you to think along with me. We're okay, we've got this written down, it's not balanced, we're good to go? So we could do one of them last, and you're right, there's 2 of them, so it's hard to tell which one to do last. But if we take a look quickly, we'll notice already our eyes go to the H2s. Why do you think your eyes go to the H2s? They're already balanced. So you might think, hey, that's awesome. That takes care of the H's. Now this is different than the way we balanced it last time. Because if we say, awesome, H's are balanced, let's balance the O's. How many O's are on the right? 1. Oh man, there's 2 over here. If I was allowed to use half, if I had 0.5 of an O2, right, half of an O2, how many oxygen atoms would that be? If I had half of an O2, that's 1, right? If I had half of this thing, right, because O2 looks like this, if I had half of that thing, and I didn't worry about that, how many oxygen atoms would there be? 1. So I could put 0.5 right there. And now it's balanced because 0.5 times 2 is 1. And how many do I have here? 1. Now you don't have to do it that way, but it means you don't have to go back and fiddle with the H's. You don't have to do it that way, but that's just this tactic that I've learned. Now, we are not allowed to have a half, so I'm going to double everything, and that means 1 times 2 is 2. 0.5 times 2 is, what's 0.5 times 2? 1. 1 times 2 is 2, and we get the same equation that we did when we did it the other way. Now, I don't care which way you do it. You don't have to do it that way. But sometimes that saves you from having to balance double things. Remember, we don't write the 1 in. I guess if it was a test and you used my 0.5 trick and you then put a 1, I would be okay with that. Let's do another one. Sorry? Yeah, by all means. I'm not going to bring them all out. Just come and grab them, and not a big deal. Yeah, you grab what you want. Yeah, some people are wanting to just practice on the whiteboard. You could do that if you'd like. Okay. If we take a look at this one, I'm noticing that the ends aren't balanced, but look at what I've got for the CLs. I've got that 2 and 3 thing. It's not easy to balance a 2 and 3 thing, but you can do that little switch over. If I had 3, and I wanted that to be black, but it doesn't matter, 3 CL2s, because I just took that 3 and put it there, how many does that make? 6. And if I take the 2 and I put it there, how many CLs does that make? 6. So you'll notice I had the 2 on one side and 3 on the other side. I swapped them. I've now got 6. They're balanced with 6 automatically. See that how that trick works sometimes? Because sometimes you're doing the math, oh, how am I going to do that? Just swap them over, and then you've got 6. By doing that, look at what we did with the ends. They're already balanced. We're done. We're done. And that took care of the CLs. So there's that 2-3 trick that you can use. So what I'm teaching you to do is not necessarily just keep counting and counting. Think about what the thing is doing and use that little 2-3 thing. Let's do another one. So you'll notice we're getting a little more complicated, a few more atoms and that. Let's use our tactics. I don't necessarily see a 2-3 scenario, but I do see things that are by themselves. So I'm going to leave things to last, right? What am I going to balance last? Absolutely last. The last number that's going to go in is going to be in front of what? Iron. Because iron's alone, and if I change that number there, I don't mess anything else up. If I change a number here, not only do I change the iron, but what else have I changed? The O's. So I'm going to leave iron for last. What am I going to do second last? The hydrogen. Because it's got H2, I might need to use a half, right? For any of those 2's, I could use a half. But it's the next simplest, so I'll do that last. So that means it guides me automatically to what to do first, right? Now, do you see what my tactics do? When you didn't have any tactics in grade 10, you just dove in and tried to balance things. But now you've got a plan to balance. Last, second last, which means O has got to be first, right? So what would you like to do for the O's? What am I going to put where? Jess, what do you think? If I put a 2 in front of the H, notice, remember, that's just a 1 right there, right? So if I put a 2 in front of the H, that's 2 times 1, that's only 2 O's. I need a 4 in front of the H. 4. I've now taken care of the O's. It really doesn't matter how we proceed at this point, whether you do H's and then F's or F's and then H's. But we'll do the H's. 4H2. I'm ignoring the O right now because I'm not concerned. Yep, what do I need? 4. 8 and 8. What do I need now for the Fe to finish it? 3. 3 and 3. So again, my tactics give you a plan. And that's better than just diving in, because diving in means you don't necessarily get things, you get confused on what you're doing. So always have a little bit of a plan. Okay, this is fun. Okay, this looks like, whoa, right? There's N's, there's H's, and all kinds of things. But if we look closely, we'll notice we've got polyatomic ions, and we're hopefully going to notice they stay together. So you're looking for things like brackets, right? If there's only one of them, it might not have a bracket, but you could always put it in if you needed to. Somebody tell me a polyatomic ion that stays together that we see on both sides. You don't have to tell me the name. Just tell me the formula of this group of atoms that seems to be appearing on one side and also appearing on the other side. And veterans don't get to answer. All right, tell me one polyatomic ion that's staying together. Oh, excellent. The name as well. Impressive. NH4 is ammonium. See it there? NH4, there it is there. I'm now going to put brackets around it because I want to be reminded that that's a polyatomic ion. What other polyatomic ion is there in here that is staying together? What other pair or group of atoms? Yep. ClO. That's a hypochlorite, by the way, but don't worry about that. ClO and ClO. Excellent. This thing here has one ammonium and one ClO. You'll notice there's nothing by itself. When there's nothing by itself, sometimes we just have to dive in and start balancing things. But we're not going to balance individual atoms necessarily. We're going to balance ClOs. We're going to balance NH4s. We are going to balance S's because they're kind of on their own. And we are going to balance Fe's. Since we're diving in, somebody give me a suggestion. This is where you're just kind of picking something and saying, hey, let's try balancing that. What would you like to do, Amy? You're looking at the Fe's, aren't you? You're seeing this 2 here, so you're wanting to put a 2 there. I like that. That's good. That's diving in and trying something. Do you see something, Isaac? Well, it doesn't matter. Tell me something different, because we do need to keep balancing. No, because notice, see, we've got the 2 here, but there isn't a 3 there, so we couldn't do the 2-3 tactic. You see what I mean? You might have been looking at this 3 here, but it would have to be with the iron itself to use the 2-3 tactic. So we couldn't do that. But do you see why we do the 2 in that position? All right, Amy, you've already given me one, so somebody else. Do you see something else we can dive in and balance? Alexis, what do you think? Pick something. I'm going to help you. Pick sulfur. For no reason. How many sulfurs are on the left? How many sulfurs are on the right? So what am I going to need over here? Sorry? Yeah, 3. I can't hear. I just want to make sure I'm hearing the right thing. 3. Excellent. You got to balance it at some point. We've done the irons. We've done the sulfurs. Now we're left with those polyatomic ions. How many ClOs are there? Now keep them together. Don't think of Cl's and O's. Think of ClOs together. How many ClOs are on the left-hand side? Jess? 6. There are 6 ClOs. That's a 1. So how many of these things do I need? 6. 6. Notice how we're not bouncing chlorine by itself and oxygen by itself. That's going to get us all confused and messed up. And because the ClOs are staying together, we can do that. Last is the NH4s. How many NH4s are on the left? Don't think of the N's and H's. Think of it as a whole thing. NH4. Stephanie, what do you think? How many NH4s are in this thing? No, you're thinking, I don't know what you're thinking. So she's thinking 4 times 3 for 12. But the 4 is part of the NH4. And we're not worried about what's in the brackets. 6. 3 times 2. Okay? Because the NH4s are staying together. Does that make sense? How many NH4s do we have over here? 6. Because remember, there's a 1 right there. Hey, that was already balanced. That's done. That's done everything. So we just kind of dove in. So if you have polyatomic ions, don't tear them apart. Now, sometimes a chemical reaction does have the polyatomic ion get torn apart. then we've got to treat them as their individual atoms. And you'll be able to tell that. If this NH4 fell apart, there might be an N2 over here and an H2. Then you couldn't treat it as NH4s. You'd have to dive in and do N's and H's. And you'd do them last. Yeah? Okay, let's keep going. Okay. I brought both of the next two up, but we'll just work one at a time. And I have, I think, something like eight examples. So I'm going to do a few more, and then you'll get to work. Now, this one's special. Write it down, and then don't start to balance it yet. I'm going to show you one more tactic that deals with these. And this is a special type, and then here we can treat them again the way they were. But I'm adding a new tactic to this. All right? And I'm going to write a little something underneath. Oh, I should put it in black. 4A. This is a particular type of chemical reaction that we're going to learn about. You've already learned about this in the past, so this isn't anything new. But this is a base reacting with an acid. Does anybody know what we call it when an acid is mixed with a base? Do you remember that stuff maybe from grade 10? You put an acid with a base and it does this. It neutralizes it. Have you heard that term before? This is a neutralization reaction. For a neutralization reaction. And the way you tell a neutralization reaction is that it has hydroxides, all right, and hydrogens. That's how you tell. That's how you know. For a neutralization reaction, you do two things. Balance the water last. Always leave the water to the end. The second thing, treat the water as a hydrogen bonded to a hydroxide. Okay? And that's what water is. It's when you take a hydrogen ion and stick it to a hydroxide ion, it makes HOH. We know the formula for water, HOH. So if you have a hydrogen and a hydroxide, you get a water. Okay, so there's the tactic for this. Do the water last and treat it like it's a hydrogen and a hydroxide. So if we're going to do the water last, what are my options to balance first? What things am I going to balance first if I'm going to leave the hydrogens and the hydroxides to the end? Sorry? I can't hear. SO4, the sulfate, and what else? The magnesium. Doesn't matter which one. Let's do, are they both? What are we finding here? Are they both already balanced? Mg, Mg, SO4, SO4. Excellent, we've done that. That's awesome. Let's now put together some waters. Remember, when we build the water, we're taking a hydrogen and we're putting a hydroxide together, and that's making a water. How many hydrogens are there? And how many hydroxides are there? So how many water molecules am I going to be able to make? Two. Because one hydrogen, right, plus one hydroxide makes one water, right? One, and one. So two hydrogens and two hydroxides are going to make two waters. And you know why everyone wants to say 4? Because you look at that number right there. That's what you're looking at, and you're trying to multiply it or something. But if we think of it as an H with an OH, one hydrogen plus one hydroxide makes one water. Two hydrogens plus two hydroxides make two waters. Are we convinced of that? 2. And that should have been red. 2. Okay? All right. The last ones that I'm going to do as examples are what are called combustion reactions. We're burning something. We're going to talk more about a combustion reaction later on. But a combustion reaction always has a fuel at the beginning that contains carbon and hydrogen. It's going to make carbon dioxide, water, and we have to mix with it some oxygen. If I'm using my tactics, what am I balancing last? If I'm using my little plan of action, what do I balance last? Yep, the oxygen. Notice it's an O2, which means I may need a 0.5 to make it work nicely because I might need a half of an O2 if I need an extra O, right? That's when the 0.5 comes in. My personal preference, C's first, H's second, then O's, because it's always written down as C something, H something. So, how many carbons? So, how many carbon dioxides? How many carbons are in each carbon dioxide? 1. 1. 1. It's balanced, right? That's done. How many hydrogens? 4. How many of these waters am I going to need to get 4 hydrogens? 2. Now we need our oxygens. How many oxygen atoms are in this? 2. How many oxygen atoms are in these 2 waters? 2. 4. How many O2s do I need to make 4? Yep, 2. 2. Always do it in that order. By the way, notice, because there's only 1 carbon in carbon dioxide, the number of carbons will always be the same as the number of carbon dioxides. Because there's 1 and 1, right? Because there are 2 hydrogens in each water, take the number of hydrogens and divide it by 2. And that'll always be the case. Let's do a couple more and then I'll let you work. Those 2 are the last ones. C's, H's, then O's. Start with the C, figure out how much you need. Start with the H's, figure out how much you need. Add the O's, work your way back to figure out how many O's you need. Do it in pencil or on a whiteboard with a marker. Always C's, H's, O's. Did you give it a shot?
Yeah.
Let's see.
But you need a half bit.
Let's see what you got. 2, 3. That's awesome. So how many O's are there in this in these 2 CO2s?
5. 2. Oh. 4 right
Yep,
there.
4 right there, right? 4 underneath. And how many O's are from those 3 waters?
3.
Right, a 3 underneath. How many in total do you need?
7.
7. If I'm counting by 2s, how many can I get to easily?
8.
I could get to 8. How many would I need? How many O2s would I need to get to 8?
4.5.
Just 4 would get me to 8.
Oh,
But I only need 7, so let's dial it back by a half.
so you would need 3.5.
See that logic that we did there? And then we're just going to double all the numbers to get rid of the half. Okay, let's work this one through. And, yep, Bethany can feel the pressure coming on because I could tell she doesn't like doing those little multiplication things in her head, so we're going to work her through. 2 C's. What am I putting out front here, Bethany? 2. Nice. 6 H's. What am I putting out front here? 3. Nice. So how many O's have I got on this side? Or you can add them up. Or did you figure that part out? You don't like the O's, do you? So 2 times 2, how many O's? 4. 3 times 1, how many O's? So how many in total? 7. Now, if I can only count by 2's, I can get myself to 6 or to 8 quite easily, right? So let's get ourselves to 6. How many O2's would you need to get to 6? So you'd need 3. But you need 1 more. So if I'm allowed to use a fraction, how much more do I need? A 0.5. You see what I mean? So because we're at 7, we can get to 6 easily. By 3, we need a 3.5 in that one. See how we got there? Now we can't technically leave those. So what we do is we just double all the numbers. This was a 1, so what does it become? 2. This is a 3.5. When we double 3.5, what does it become? 7. Oh, and use your calculator if you have to. 2 times 3.5. 7. This becomes a 4. This becomes a 6. Okay? The 0.5 trick works when you're dealing with an O2, because sometimes you need an odd number. Then you need that little half. So then do a 2 count till you get to right below or above. That's what you did. And then bring it back or bring it up by a half. Now this one's a little mean, because notice we've got 1 O already taken care of in this fuel molecule, which means we can dial this number back by a half, because we've already got a half built in there. So let's use the same tactics that we did before. C's, H's, and O's. And I'll start with the black one. How many C's on the left? 1. So how many of these do I need? 1. Got it. Good. How many H's are over here? 3 and 4. So how many of these do I need? I need 2. I need 2. So how many O's in this guy? 2. And how many O's do this? 2, which means 4. Now you might think, awesome, 4 works well. I'm gonna put a 2 in there, but there's already 1 over here. So if there's 1 here, how many do I need in here to make my 4? I need a half at some point. I need 3 O's, right? So if I do my 2 counting, 2, what do I need to then add on top of that 1 O? 1.5, 1.5, 1.5. Because that extra O was in there, it messed us up. Okay, once we've done that, we double everything up. 2, what's this become? 3, 2, 4. And if you've done the logic correct, it will be balanced. There is no need to, to count all those atoms up all the time. We're thinking logically. Okay, so that's the end of the lesson. So I'm going to guide you to the question sheet, but first I'm going to shut down the recorder.